Hey guys, it's Bob Moriali here, and today I'm talking with Brian Tooley from Brian Tooley Racing, and we're going to be discussing cylinder heads. So you want to stay tuned and watch for that. Hey guys, welcome back. I'm here this morning with Brian Tooley via Skype. Hey Brian, welcome back.
Morning, Bob.
Thanks for joining us again, man.
Thank you. Thanks for having me.
Absolutely. So last time we talked about camshafts quite a bit. Today we're going to be discussing cylinder heads. Right?
Yeah. A topic I actually know a lot about.
A topic you do know a lot about, right? Yes.
More so than camshafts, I would have to say.
Oh, wow. See, I think that'll surprise a lot of people. So before we get into the tech stuff, I'm just curious, how did Brian Tooley Racing come to life? Because I think a long time ago you used to work for some of the other companies like Holly and whatnot, am I right?
Right. Well, what happened was I started a cylinder head porting company in 1992 in Bowling Green, Kentucky. And then in 93, I got hired into Holly and was there until 95. And then 96, went back to self-employment by 2000, and that was with Total Airflow steel. 2001, I bought a 5-axis simultaneous CNC machine. Now, 2001, to have a true 5-axis simultaneous CNC machine was a big deal.
That was a big deal.
People that didn't believe it to the point that they would travel from states away just to see it. Those were quite rare back in the day. And that was a Fadal 6020 that I bought, 6030 rather. And I sold that business to Summit Racing Trick Flow in 2004. And then from 2004 to 2010, I oversaw cylinder head development at Trick Flow.
Cool. Okay, so that was one of your core things that you worked on for a long time.
Yes.
Excellent.
Yes.
Excellent.
And that cylinder head knowledge is what I think has helped me in the camshaft part of things.
You know, so many racers you talk to who have been, doing this 20, 30 years, they all tell you, hey man, there's power in lots of different places, but really the power's in the heads. Would you agree with that? Would you agree with that?
You said power is in the heads?
Yes.
Absolutely. Yeah, I could do a camshaft that picks up 20, 30, 40, maybe 50. I can do cylinder heads that pick up 75, 100. There's definitely way more power in cylinder heads than camshafts.
Okay, so
it depends on application, I guess I have to say. If you've got a fifth gen Camaro, then not so much.
Sure.
Because it's already got too big of a head on it.
Gotcha.
But for certainly power adder applications, cylinder heads very, very important. More important than camshaft.
Yeah, I had seen that quite a bit on the LS1s and the LS2s, and I think as they moved towards the rectangle ports, things kind of didn't gain quite as much.
Right.
Yeah.
Exactly.
So I actually have a question from one of the viewers who had watched, I think, last week's episode, and they had said their question was, why has the overhead valve design, the pushrod engine, really, why is it still here? And why is it still competitive with, say, a Ford modular motor with, 4 cams and a bazillion valves?
Well, when you look at the Ford 4650, single overhead cam, door overhead cam, I guess you'd have to narrow that down to door overhead cam. When you compare that to the LS, I mean, the pushrod design has changed, obviously has stayed, the pushrod design has stayed because of simplicity and cost. Clearly, 4-valve per cylinder, dual overhead cam, that is definitely a more efficient package. The only reason the Chevrolet has really stayed is because you can physically get a 427 engine that's smaller than a 5-liter engine.
Right. Yeah, and
so
package-wise, you mean?
Right, package-wise. So, and you're only going to make so much horsepower per cubic inch. I feel like with a pushrod engine, with any given, constraint in terms of compression ratio or camshaft design, things like that, RPM ability.
Right.
The dual overhead cam is definitely a better design, no doubt about it.
Let me ask you a question, because a lot of our Ford guys, they always go, well, if our engine was the same size as an LS engine, we'd have you all beat. And, looking at the numbers, I think that might be true. What do you think?
It's absolutely true.
Okay.
No doubt about it.
All right, so you hear that, GM guys. We just should be happy that Ford makes tiny motors still.
Yeah. If Ford comes out with a 4.400 bore spaced block like Chevrolet's got,
right,
we're all in trouble.
Yeah, exactly.
Buying Fords.
Exactly. Well, good for Ford, and maybe GM will have to make an 8-liter. I don't know.
Yeah.
All right, so next question actually was, what is the most important part of cylinder head design, selection, and in that nature?
In my opinion, the most important aspect would be proper sizing.
Okay.
Number one problem I see is everybody is on this bigger is better mentality. And the bigger it is and the more air it flows, the better it's going to be.
Right.
And nothing further from the truth.
Okay. So expand on that for a little bit. Why is that so important?
Well, what makes the cylinder head make power is efficiency. And we measure efficiency with a simple calculation, coefficient of discharge, which we kind of touched on in the camshaft video. And that coefficient of discharge formula, I just like to draw it out here real quick.
Yeah.
Real simple. It's airflow at each lift point divided by the valve curtain area. And that curtain area is the valve diameter times pi times the amount of lift, right? So that gives you that valve curtain area. So what you end up with is you end up with CFM per square inch with this.
Which is efficiency.
That's efficiency.
Yeah,
right.
Absolutely.
And so in what we look at in the cylinder head, because people look at, when you got, 100 lift, 400 lift, 600 and 700 lift, everybody focuses on these numbers up here. They want to see, if this thing doesn't flow 400 CFM
right.
or more, then
Right.
it must be a piece of crap.
Right.
They realize that, if this thing flows 300 CFM, if this head flows 300 CFM before, it may only flow 360 up here.
Mm-hmm.
But if this big 400 CFM head, because of valve shrouding, only flows 280,
Yeah.
it's going to make less power.
Sure. Absolutely.
And the other aspect, particularly with boosted engines, is the exhaust valve.
Mm-hmm.
Exhaust valve location, exhaust flow. Because when you get that intake valve that big, like in an LS7 application, you have to move that exhaust valve very close to the cylinder wall.
Mm-hmm.
I'd like to actually tell a story. Hopefully this isn't too lengthy.
That's
Maybe
okay.
you have to crop it out later. But whenever I was at Trick Flow, we were developing the LS3, LS7 heads, and we developed the LS3 head first. The LS3 head was simply LS7 valve geometry, 12 degree LS7 valve location, with the exhaust valve moved away from the cylinder wall 50 thousandths, so it cleared the smaller bore.
Okay.
And so we developed that exhaust port first. Well, when it came time to do the LS7 exhaust port, I thought, you know what? This is going to be simple. I'm going to take this good exhaust port, I'm going to move it 50 thousandths in location, I'm going to rotate the flange 50 thousandths, and my exhaust port's going to be done.
Right.
So we did that. We cut it in a we had these, we called it wood. It's a high density
Sure.
board material. And we cut that exhaust port in that head, and it was terrible. That 50 thousandths change in exhaust valve center line absolutely
everything.
killed the exhaust flow in the head. So that's why, people see an LS7 head and they think, oh, this great big intake board, this is what I need for boost. You got to get it out.
Yeah.
And here's a perfect story. Guy works for me, Jerry Kokenauer, has a C6, Z06, F1X, had Trick Flow LS7 heads that we did, and we changed that to the Trick Flow 245 cathedral port heads, and it made a lot more power, but more importantly, it lost boost with the cathedral port head. Everyone knows that boost is just a measurement of restriction. Well, if you put a smaller head on that engine and it loses boost, it's not because of what happened on the intake side.
Right.
It's because of what's going on the exhaust side.
Right. Right.
So that's something that people lose sight of in these big heads, is that exhaust port is the one that's suffering for that big intake valve.
That makes sense. It has to go somewhere.
It has to get out.
It has to get out.
So you have to have a good balance between intake port efficiency and exhaust port flow.
Absolutely. So you get yourself a giant intake valve, you end up with an issue on the exhaust side now because you're imbalanced, and you're no longer making great power.
Exactly.
Yeah.
What you gained on intake,
Yeah.
you've lost on exhaust.
Right.
And you've come nowhere.
Yeah, that makes perfect sense. And what you talked about earlier with the lift numbers there, I used to do a lot of cylinder head flowing and testing and porting too. And I would always tell people, quit buying based on this magic flow number and It's just you look at it and from a simpleton terms, you say how much time does it actually spend at 700,000th lift? It doesn't.
Exactly.
It's not there all the time. It's you spend all that time sweeping through to get there, and then you're out. So it was always more important to me to look at the same thing you said here and go, you know what? I need some good flow in the mid-range to make the best power, because it's going to spend the bulk of its time there.
Exactly.
Yeah.
The other thing I'd like to touch on would be exhaust flow and low lift flow, because once again, when you start talking about flow numbers, people are all focused on these big numbers. If you draw out numbers down here, and you start asking people, okay, for intake flow, what's a good number here? For exhaust flow, what's a good number here?
Right.
And for a hydraulic roller cam street strip car, you don't want this on either side.
Right.
This is bad. This is going to cause intake reversion. This is going to cause loss of low end torque. Because people don't think about how far that piston is back up the bore on the compression stroke before the intake valve even closes.
Sure.
You can lose a ton of torque with too much low lift intake exhaust flow. Well, and similarly, particularly with a supercharged engine, you also don't want too much low lift exhaust flow.
Right.
An interesting thing that we do, we do these LSA cylinder heads, and all the boosted heads we do, we put a 50-degree exhaust valve job on. Well, that 50-degree exhaust valve job will drop this 100,000 flow number at least 10% every time. And people think, well, that's bad. It's like, no, that's good.
Right.
Because the blower is blowing that air in the cylinder, and this reduced low lift exhaust flow keeps you from blowing it out the exhaust.
Yes, that makes sense. Yep.
I had a customer that we did a set of LSA heads for. He tested them back to back on the dyno. He gained 50 real horsepower.
Wow.
Most importantly, he didn't lose any boost.
Right.
And another friend of mine who was very knowledgeable, he said, that's impossible. There's no way those two can coincide. If he picked up 50 real horsepower, he had to lose boost. And those guys are very sensitive to boost.
Sure.
Now, when he didn't lose boost, because we reduced that low lift exhaust flow
Sure.
to the point that what he's reading on his gauge wasn't reduced, because we're putting that air in the cylinder, not out the exhaust during overlap.
Absolutely.
So that's a very, very important thing that people lose the sight of. So if people would start focusing on the 100, 3, 4, and 500 flow numbers and forget the 600 and 700 flow numbers, they would have much better cylinder heads. In particular, if they did the coefficient of discharge calculation to just figure out, which head is most efficient, they would have much better cylinder heads.
And is that conducive to the intake to exhaust flow ratios that you see a lot of people using when they're shopping?
I never have got real hung up on intake to exhaust flow ratios. For most applications, most wedge head applications, those stay pretty well in balance. I think you want to be in that 60 to 80% range. An interesting place they do get out of balance: dual overhead cam, 4-valve, or cylinder heads.
Really?
You'll see exhaust numbers of 90% of what intake is.
Wow. And how is that good for them? I mean, usually you go,
It's not good for them.
Okay. All right.
And that's another class of guys who we've gone and put 50-degree exhaust valve jobs on their heads, and they picked up a bunch of power.
Sure.
Just because they're not blowing it out the exhaust during overlap.
Sure. No, that makes perfect sense.
Yeah. Of course, they tend to run less overlap also compared to a wedge head. So,
right.
It's not quite as detrimental. But that's also why you see, you may put naturally aspirated cams in a 4-valve engine, 4-cam engine, and gain 20 horsepower, and then you put a boost on it, and now those same cams are only worth 10.
Right.
It's because a lot of that boost is going out that exhaust port.
So they're trying to make it into a jet turbine or something to force the air out the back and propel the vehicle.
Yeah.
Never understood that. No, I never really got that, man. So if I understand all this properly, then the best thing we can do is to properly pick. We talked about valve size. We talked about some coefficients, but what about runners in terms of intake and exhaust runner, size?
That's a great question. I don't get too hung up on intake port volume. That intake valve diameter controls how that cylinder head acts way more so than the intake port volume itself.
Mm-hmm.
But on the exhaust port, it's kind of the opposite, because you want that exhaust port as small and as efficient as possible.
Okay.
And the worst thing that you can do on a boosted application is make that exhaust port big,
mm-hmm.
because then it's lazy, it's inefficient,
right.
and it just doesn't work well.
Right. Now, do you see a difference when looking at a particular type of supercharged vehicle versus turbocharged?
They both need an efficient exhaust port based on what I've seen.
Okay.
I'll tell you an interesting, talking about exhaust flow and exhaust port volume, interesting test we did at Trick Flow. One of the first back-to-back testing we did was we developed the 5.7 heads, LS1 heads,
mm-hmm.
and we took them to the dyno, the engine dyno there, and we had the Trick Flow 215, the AFR 205, we had some of the TEA CNC ported cylinder heads, and we wanted to test inch and 3/4 and inch and 7/8 exhaust,
mm-hmm.
headers rather. And so we put the CNC GM heads that had the stock 155 exhaust valve, but when we back-to-back tested the headers, the inch and 7/8 was significantly better.
Mm-hmm.
Okay, we tested the Trick Flow heads with a 1.57 exhaust valve, and honestly, both headers made about the same power.
Mm-hmm.
Then we tested the AFR 205 heads, which actually has a really big 88cc exhaust port. That's big for an LS1.
Yeah.
Most people don't know how big that exhaust port is.
That's big.
And when we tested that back to back, the inch and 7/8 headers actually made less power.
Wow. Okay. Yeah, that makes sense.
And in my opinion, it's because it was over scavenging during the overlap.
Okay.
Because if you scavenge, your intake air charge out the exhaust during overlap, it's going to make less power.
Mm-hmm.
And probably that leads into another interesting story. Whenever we developed the Trick Flow 225 heads, we used the same 1.57 exhaust valve on it.
Mm-hmm.
And guy out in California, C6 Corvette, LS2, bought one of the first pair, and he had Lingenfelter CNC heads, 1/600 exhaust valve. Mm-hmm. And he installed the heads, he data logged it, and his airflow was down. Mm-hmm. It was down a fair bit, and he called me. He was very upset. He said, I'm moving less air through the engine. Mm-hmm. I said, well, don't get too upset yet. Take it to the dyno, see what it makes. This LS2 already made 480, so it was, it was making pretty decent power.
Yeah. So
he takes it to the chassis dyno, it makes 507.
Wow.
And he comes back, he said, how can the airflow through the engine be down, but it be up 27 horsepower? Mm-hmm. And I said, it's because you're putting the air in the cylinder, not at the exhaust port during overlap.
Sure.
Now, whenever you have unlimited induction, whenever you've got a sheet metal intake and unlimited induction, that doesn't really come into play. Mm-hmm. But whenever you've got a limited intake like a fast stock intake, those intakes become somewhat of a restriction, and so you can't over scavenge or you will lose horsepower.
Sure, that makes sense. Now you're pulling from the intake to get it out the exhaust.
Yeah.
Which makes no sense.
Right.
Yeah.
Yeah.
You've lost a lot of that. Cylinder filling. So talk about cylinder filling in relation to cylinder heads.
Yeah, well, I mean, cylinder filling is just it's a derivative of everything we've talked about, right? Mm-hmm. I mean, we talk about efficiency, we talk about not having too much low lift intake flow or exhaust flow, particularly cylinder filling at low engine speeds, because that's something a lot of people don't touch on until they build a big, let's say, naturally aspirated engine, mm-hmm. and then it's a dog down low, or they just built an engine in general and they've got too big a cylinder head and it's a dog down low. They're like, why is my engine down 50 or 100 foot-pounds of torque at 4,000 RPM compared to like a theta port head? And I tell them it's because here's your stroke of your piston. Mm-hmm. That piston's almost halfway up the bore before the intake valve finally closes.
Yeah.
Well, at low engine speeds, you're pushing that air right back into the intake port. Mm-hmm. And that's why big intake valves,
not necessarily right. Yeah.
That's why they suck at low speed torque. And the other thing that happens to you tuners is you guys have these big heads or these big valves, and you've got somebody out here trying to tune this thing at 2,000, 22, 2,300 RPM, and it's doing all kinds of weird stuff.
Yep.
It's because of what's happening at low lift.
Yeah.
The intake valve is too big.
Yep.
Intake port is too big. You've got big time intake reversion, and it's frustrating.
I'm really glad you put that out there, because we do a lot of tech support, for our shop owners. And I would say a lot of them are relative to what you just said. And you know, in our experience, what that means is we're tuning around a mechanical issue. And the best result for that is to help improve the situation. That's the best we can do with a laptop. And unfortunately, you know, the customer base, they don't always understand that. They don't always get the fact that, you know, man, the guy with the laptop can't, it's not a silver bullet. We can't fix, you know, scavenging issues or reversion issues. And why does the car chug so bad when I'm at, you know, 6th gear, 40 miles an hour? I used to be able to do it with my stock cam. That's probably 1 ticket out of 10. And you'd have to go through explaining how to build the best torque we can down there with the mechanical limitations they've imposed on themselves. And guys don't want to hear that, but it's the issue of bigger is better. That's the counter to that.
Yeah, and when you get these LS3 engines, well, the intake valve is too big.
Mm-hmm.
You know, it goes back to our cam discussion of intake valve closed.
Mm-hmm.
You know, if you're some dummy that's got, you know, this type of intake valve closed,
Mm-hmm.
you're going to have tuning problems.
It's going to create an issue.
Your combination is going to suck. It's not going to have good low speed torque. You need to be down in this range.
Mm-hmm.
You know,
yep. It's funny because, you know, when you talk to the end user and they, you know, you ask them up front, what are their goals? What is it they're looking to achieve? And they want great drivability and they want, you know, massive, you know, 1,000 horsepower and these things that are kind of on opposite ends of the spectrum. I tell them, you know, in my experience, we need to get you a camshaft that's somewhere in the mid-range here so that you can have that mid and low range power that you're going to love as soon as you leave a parking lot. And guys don't get that because they get hung up, in our world, they get hung up on the dyno numbers.
Yep.
And,
absolutely.
you know, what's that peak number? You know, and I don't know, it's so awful because you're trying to explain to these guys, you know, you only made 400 at the wheels. Oh my gosh, you only made 400 at the wheels. But, you know, you made 350 of that all the way down to, you know, some obscenely low RPM, and this thing's going to be a rocket and it's going to tear up your buddy's car that makes 500 to the wheels. It's just the hardest thing for people to comprehend because we're guys, usually, and the guys are the ones we don't get it and think bigger is better, and I have to make 500 at the wheels or my car is a turd. It's just it's a constant struggle for not just us, for the shop owners, for everybody watching this.
Well, even these cylinder headquarters, let's face it, to get flow numbers here, this is technology.
Right.
This is valve job, combustion chamber technology.
Yep.
To get this number, all you got to do is make it big.
Yep. Absolutely.
So this number is far easier to get than this number.
Yep.
Particularly when you're talking about using a smaller and smaller intake valve.
To make it happen. So, a question we get a lot is velocity versus CFM. And how mutually exclusive are they?
Well, you know, I get asked a lot about velocity,
Mm-hmm.
and I mean, the coefficient of discharge formula is a measure of velocity. But I did a lot of velocity valve probing in the years I did cylinder heads, and finally did the velocity valve probe where, you know, we have the valve and we have the whole EDM through the stem and a whole EDM to the 45-degree face of the valve, and we've hooked that up to a manometer, and we're taking measurements every 45 degrees in that intake port. Well, interestingly enough, when you get that velocity almost exactly even at 300, 400, 500 lift, guess where your flow numbers are?
Yeah.
They're really high.
Yeah.
Okay?
Mm-hmm.
You know, so those two are one and the same. So, you know, people talk about velocity in a port, but you really need to measure the velocity at the valve, you know, like what I was describing with that velocity valve probe.
Sure.
And because it's interesting what you find, because everybody says, well, port stall is where the intake air detaches from the short term.
Mm-hmm.
Bullshit. It never happens.
Right.
Let me tell you what happens. If this is your cylinder, and this is your intake valve, and this is your intake port, people are going to say, oh yeah, the airflow is detaching, it's all over here.
Mm-hmm.
No, guess what happens? It all ends up right here, close to the center of the cylinder. So as you're flowing this thing on the flow bench, and you're looking at the velocity around the circumference of the valve, you'll actually see the airflow over here drop off.
I've seen that.
When that increases, right? And so people say port stall is the airflow detaching from the short term. No, port stall is a gross imbalance of velocity around the circumference of the valve.
Yep.
That's what port stall is.
Yeah, that makes perfect sense.
And port stall, in my experience, back-to-back testing, hydraulic roller cam, street strip stuff, port stall, not very important.
Mm-hmm.
You know, people talk about getting these cylinder heads to flow to 700, 800, 900 lift. if that head flows to your peak valve lift, that's all it needs to do.
Right. Right.
And,
Yep.
and people talk about flowing heads at 50 inches of water or 100 inches of water and different stuff. You know, I think it's, 28 inches is still a good number to flow heads at for street strip. You know, we're not doing 10,000 RPM cylinder heads here. We're doing sub 7,500 RPM heads.
Sure.
And I think the number one problem in the industry as a whole, no one does the back-to-back testing.
Yeah, it's true.
I bought a chassis dyno in 2001. We back-to-back tested stuff. So in 2001, I had a chassis dyno and a CNC machine.
Yep.
So guess what we did a lot of?
Yeah.
Did a lot of testing.
Yeah, that's what you're supposed to do for that sort of result that you're after.
Yeah. And, and obviously, we did enough to impress Trickflow, and they bought the business, and there we had 2 engine dynos, so then we got to do even more back-to-back testing.
Sure.
So the number one problem in this industry, for specifically the hydraulic roller LS engines, no one does the back-to-back testing.
Sure.
Number one problem.
So why do you think that is? Do you think it's just a monetary thing or marketing or
resources and money?
Yeah.
Yeah, because let's face it, if you've got a CNC machine, chances are you don't have money falling out of your pockets.
That's true.
Chances are you're a very busy guy. You don't have time to go to the dyno and get a bunch of heads together and back-to-back test that stuff.
Sure, absolutely.
The resources we had at Summit Racing, unbelievable. Oh, you want to go test this head? We walk across the street and get the cylinder heads out of stock and put them on the dyno.
That's awesome.
Yeah, I mean, we tested everything.
Yeah. Well, that's how you make progress, right?
That's right.
That's exactly how you make it.
But I guarantee you, 90% of the students that have just graduated from some cylinder head 40 class somewhere in the U.S. will tell you that this whole coefficient discharge thing, it's all bunk. They've never tested one set of heads back-to-back on a hydraulic roller cam.
Sure.
But they'll tell you that it's bunk.
Right. Absolutely.
Yeah.
No hands-on experience.
And they need to do the testing.
Yes.
They need to do the back-to-back testing.
Absolutely. Well, Brian, I have one more question from a viewer, but I think we're going to actually segment that off and create a separate Tech Tuesday for it, because I think it's that important. And I'll preface it with you now, and I'll tell you guys now. The question really was relative to detonation. And, cylinder heads, detonation, and that arena by itself. And I was thinking we create that as a separate video, simply because we see that a lot on the dyno, and as tuning, guys, we have to be the guys that deal with it. So we're going to go ahead and just close out this video. And Brian, thank you for hanging with us and chatting with us so long today.
Yeah,
absolutely, thank you. And all you guys watch and stay tuned. Next Tech Tuesday video, we're going to go ahead and talk with Brian some more, and we're going to specifically cover detonation in relation to cylinder heads, head design, selection, and then also on the tuning side as well. So thank you for watching, guys. And Brian, thank you for hanging out with us again.
Thanks.
Absolutely.